Okay.
Here's a classic logarithm word problem. It says the population of a town is modeled by this equation right here, where t equals 0 represents the year 2000. So in 2001, t would be 1. In 2005, t would be 5, etc. Okay? So let's just analyze this equation. It's saying that p equals 4350 times e to the 0.0315 t. And what that means is this right here, when t equals 0, when the time is 0, meaning in 2000, because that's when the time is 0, time equals 0 in 2000. This whole thing would just go away. It would become 1, because e to the 0 equals 1. Anything to the 0 equals 1. And so p sub 0, meaning at 0, is 4,350. Meaning, in the year 2000, this would be a question you might get on the ACT or something. What's the population in the year 2000? And that's not a trick question. It's just, do you understand what that equation represents? And the answer would be 4,350 people. So, but now what's happening is they're saying, according to the model, in what year did the population reach 13,000? So now my p, this is the new population. So p is 13,000, and now I need to solve this equation, e to the 0.0315 t. I have to solve that equation for t, and there's my t right there. Well, how do I get my t out of the exponent? This is where logarithms come in. So first of all, I'm going to get rid of that by dividing it, and I even like to leave it in fractional form. Now I'm going to get rid of, this is the trick here, to get that whole thing, remember that's 0.0315 t. To get that whole thing out of the exponent, I don't divide by e, that won't do anything. I have to take the natural log of both sides. So when I take the natural log of the left side and of the right side, my new right side, this whole numerator is going to come down front. That's one of the properties of logarithms. So here's my equation. The natural log of 13,000 over 4,350, I'm going to leave it like that, equals 0.0315 t times the natural log of e. And what's the natural log of e?
1.
The natural log means log base e, so the log base e of e is just 1. And so now, see how nice it is? I just have t almost by itself. All I have to do now is divide by this number, 0.0315, and there's my answer, my exact answer. Punch that carefully in your calculator, and you get t equals 94.87 approximately. So it says, according to the model, in what year did the population reach 13,000? Here's another trick. In what year did it reach it? Well, it was almost through the entire year. It was 87/100ths through that year, 94 years after 2000. So in what year did it reach that? You actually don't round it up, you round it down.
So
2094. In the year 2094, toward the end of the year, they may even specifically ask you, was it toward the end of the year or toward the beginning? And because this is 0.87, it actually reached 13,000 toward the end of the year. Now, here's the second part of this question. It says, according to the model, in what year did the population reach 1985? So now this is a different question. I'm sorry. According to the model, what was the population in 1985? So this is kind of tricky because this is going backward. So in 1985, t equaled, that was 15 years before the year 2000. So t equaled -15, and we're using this and kind of going backward. And so your answer would be, let me wipe all this clean. Whoops.
yeah.
So I'm just plugging into my equation. P equals 4350 times e to the 0.0315, and this is easier. All I have to do is plug in negative 15 for t into that model, and then simplify it with my calculator, and I get approximately 4340.8.9. So you might want to round that up. But according to the model, what was the population in that year? The population was not much less. And the reason the population was not much less was because, check that calculation mistake, it's actually 2,711.97. So you could approximate that to 2,712 people. So that would be the answer to part B.